Okay, so last time we showed how using maximum likely estimates we can get the estimates of our beta j's and also some variance on that. And now we're going to use that for inference. So as long as your data is sufficiently nice, so we need a large number of experiments, or within each one, large numbers of fixed trials, then we can see that the approximate distribution of beta j hat, so that's our estimate in our studio, is going to be approximately normally distributed with a mean of beta j, so it's an unbiased estimator, and a standard deviation that's going to be the square root of that complicated thing. But all you're going to do is you've got this variance covariance matrix, which is the Fisher information. You take the inverse and you look along the diagonals. So that I beta hat minus 1 with the brackets jj is the jth diagonal element of the inverse of your Fisher information, which we got anyway to calculate these coefficients. It was part of the way we actually estimated it. So for example, if I wanted a 101 minus alpha percent confidence interval beta j, I would go beta j hat plus or minus z alpha over 2, so 95 would be 1.96, the square root of that diagonal element. And that's the thing that comes in that table, and we'll see later on. I'm going to do a video on the BTools data, and we'll actually see that. Sometimes we don't want to do hypothesis testing or confidence interval for a single beta j, we'd like to do lots of beta j's. So imagine this scenario. I've got a model M, and I've got a load of betas, beta 1 up to beta p. Then what I'm going to do is I'm basically going to say, we'll take the first load, we'll split the model, we'll take a load at the start, which are fine, we'll go from beta 1 up to beta, we'll call it P0. And then we're going to take all the betas after that. So we'll have beta P0 plus 1, plus 2, all the way up to beta P. We're going to say, maybe they all equal 0. So it's a nested model. We've got this full model with lots of betas, and then we've got another smaller model when a lot of the final betas are equal to 0. We might want to test that. And what we do is we do a likelihood ratio test. So you work out the log likelihood for your full model, which is L beta hat. Then your smaller model, L beta hat 0. You get these two, you take 2 minus the difference, and that number we call G squared. And that will have a chi-squared degrees of freedom. So if the null hypothesis is true, that is, all the ones should be 0, then that G squared will be a chi-squared with P minus P0's degrees of freedom. And then all we need to do is we just look up our appropriate cutoff point. We also, using that idea, have a thing called a deviance statistic. You'll see it's called the residual deviance in the model. And what we're doing is we're taking our model that we fitted, and then we're going to do basically our likelihood without restriction. So for example, in the case of our Beatles experiment, what we do is for each individual experiment, we would set pi I to be the observed proportion. So every experiment gets its own. So you basically overfitted it. Every experiment gets its own. And that's the L hat that we have in this thing. So we can do hypothesis testing of individual coefficients. We can test a lot of coefficients at the same time by having these models and compare them. But then we have to say, well, how good is our model fit? And there's two approaches we can do. We can do a formal approach using hypothesis testing, so using what we just learned, or we can do our standard, look at residuals. So one thing you could do is you could say, I've got two models and I want to compare them, and we can now just do an ANOVA test to compare our two models. So you can get a more general one, and as long as they are nested within one another, that is, you can get from one to the other by setting parameters equal to 0, then you could do your ANOVA. If you can't do that, you can do an AIC, and later in this course we'll talk about AIC, Attack as Information Criteria. The less formal thing is you just do some plots. You plot your residuals from your model fit against your fitted values, etc., and you look for any deviation to try and do it. And we'll have a nice example of this in the BTools case study. What sort of residuals should we do? Well, there's two sorts you could do. You've got the Pearson, where what you're doing is you're taking your observed minus your expected value divided by your standard deviation, where we're using the idea that we think it's binomial to get them. So that's the Pearson residual. The other one you do is what we call the deviance residual. So this is very complicated, but basically for each observation, you're saying how much does that actually contribute to the deviance residual. And both of these, what you're looking is you're plotting the residuals versus your fitted and seeing again if there's any sort of pattern there that you need to take into account. Roughly the same, but you don't quite have as much options. Often they will show you, if you do the GGLM, it will show you the normal QQ plot. And some people will use this, but remember, you don't really have normality of your residuals. What you have in your particular case is they're from a binomial distribution. But if your data is sufficiently large, we know that normal can approximate. But the main thing you're looking at is to see if there is any pattern in there you need to take into account. Everything we've looked at so far has been for group data, where we had like an experiment like the beetles, where we had like NI number of beetles, etc. But you can actually have ungrouped data where now you've got individual subjects and you'll measure where each Y value is either a 1 or a 0. This is very commonly used. You'll see this in data science next semester, where you've got this classification 1, 0 you want to predict. The problem is your residual checking, some of your assumptions of your ANOVA and stuff like that become very, very hard in that situation. Mainly because you don't have enough data to start calculating or see the patterns. It becomes we'll see examples of this in next semester. You see a lot of discretization of the residuals. There's a lot of people who looked at different ways, like binning and stuff like that, but generally it just gets very, very hard when you just have 0, 1. The group data, which is why we focus on this course, is so much easier. The other thing is, at this point, occasionally you will get data that fits the binomial, but not quite. So the idea is that once we've got our pi I from our model, we know the expected value of yi should be n pi I, and the variance should be ni pi I1 minus pi I. And sometimes you'll get it that the variance, your observed variance, is greater than what you expect under the binomial. And in that case, we say it's over dispersed. So dispersed is more spread, so it's got too much spread compared to that binomial. Sometimes it can be under dispersed as well, but over dispersed is the common one. And we'll see an example in a case study called cells, where we look at this. And what you do in that way, you improve your model. So the thing about the binomial is it only really has these two parameters, the ni and the pi I. And so sometimes it's not enough to explain that extra variance. So there's things like the quasi-binomial that you can use to actually improve that model. But what you can do is you can look for this over dispersion. You can say, is the mean and the variance what I expect? If the variance is more than you expect in the observed data, then you account for it in your model. And this is the example that we will look at in the cells. The final thing is, I'm going to give you an example here of where things can go wrong. Because the problem is, R will fit logistic regression even when it shouldn't do. So here I've got some simple data. I've done Y on X. I've fitted the model. It all looks fine. But you notice a couple of weird things that you want to start being worried about. First of all, your standard error is huge. All your p-values are really, really large. And you start to be worried about this data. Something's going wrong. So what's the something going wrong in this one? Well, the problem is in this one is your data's too good. I've actually simulated data here that basically has a value of 1 if x is greater than 0 and a value of 0 if it's less than 0. So this data separates perfectly. And the problem is once it separates perfectly, you find that there's not a single solution. You can have an infinite number of solutions that would actually fit this okay. And because of that, you're having problems. It's not converging well. So in this particular case, you could pick it up because you could do a quick plot of your response variable, 0s and 1s, against your x. But what should you look for? Well, you're looking to make sure that your thing has converged. Because the thing is, it will just keep going, but maybe it hasn't converged. So look for warning messages. Sometimes it will say it didn't converge or it was really slow to converge. Also have a look at the number of iterations in that process that we did, the Newton-Raphson. If there's lots, you should be worried about. As I said, parameter estimates and standard errors of very large values, you should be really worried about. And probability is very close to 0, 1. So if you do your estimated, you look at your pi's and you predict, you get lots of 0s and 1s, you should be worried. But always, the thing about R is it will try and fit a model and give you results. Sometimes, as you see, those results are just nonsense. Okay, so that's it. Next, I think we're going to focus on some case examples to illustrate all this theory in practice. See you next time.